Annalena, for this nice introduction, and also, let's say, for the opportunity here to speak to my colleagues and PhD students and master students that helped me. Very welcome all. So yeah, I'll be talking about intelligent linguistic information systems from a textual point of view. And that actually had to do also with the introduction that I'm, let's say, one of the older professors in the department. I observe nowadays, and that's fine. And let me, let's say, promise you at the age that I'm 61. You may know I'm father of 4 and grandfather of 2. That you say, okay, what's there left for me to do in science? Yeah. And then, of course, I have written some papers, I've supervised some PhD students. You think, okay, would it really matter when I retire? So I thought, well, I see head of department having his doubts on that. So, but I thought, okay, I can continue with, let's say, my work in requirements in architecture, and that is fine, and we're writing a book together with Fabiano, and that will work. But I also thought, okay, why not have a project as a mission to Mars? And you see in many fields that people take those really far-fetched visions. How can we serve society with something that is really, that other domains will say, wow, that is great that you're doing that. And that is what I had it already, this idea of automated medical reporting. When you are in a hospital, when you are with a GP, a general practitioner, a huisarts, they are typing, and when you're married or have with someone in healthcare, you even have, like me, that they are late because they have to type all their reports. And that is, so can't we use contemporary speech recognition, action recognition, IoT, and whatever we would like to do in order to make, let's say, to reporting automated? Can't we, let's say, reduce the reporting time to 0? In fact, remove the keyboard from the hospital. Would that be an option as a far-fetched? And what is then needed? And that is my research currently on. And in order to link, of course, I have an architecture point of view. So this is my presentation, my overview, and I start with aiming. So the background, the starting point is architecting. My main research question is how can we architecture software applications for the automated reporting of human activity. So it's broader than, let's say, medical reporting. This morning we had a meeting with the police for, let's say, the automated reporting of warrants. That is a proces verbaal in Dutch that can also be done with this technology in principle. And we use all kinds of AI and natural language. So for those who are active in this domain of AI and natural language, please, you're doing very good work, and we need your work even more for this. And so we apply this in healthcare for the high administrative burden. Sorry. Lots of collaborating partners also beyond this. I will not go into detail. You will trust that. But this is the issue. And there are reports that they spend about, say, 20%, even 30% of their time on reporting. Essentially, we want to do 3 things. I would say, typing is cumbersome, so we want to reduce the time. Typing is intrusive. We want to improve the patient experience by removing the need to type. and typing is too shallow. All kind of details are missing. Oh, what was the heart rate again? The blood pressure, I forgot, so it's not included. But also in collaboration, I now find that when I want to collaborate with, for instance, the Utrecht University Medical Hospital or Leiden, or that they also want to use this, our technology, for getting their research data even enriched. So that, but I come back to that later. So the data that they have in the, for instance, the electronic medical record, the elektronisch patiëntendossier in Netherlands, but the records of patients, the data is often unfit for doing research. So there are many papers about that, what are the costs and what are the consequences and whatsoever. But given the fact that when you take 15% of time in the medical professionals is used for reporting, 15% is in the Netherlands, that costs 5 billion euros per year. 50% of so many people, that costs so many billions, and that's a very easy calculation. But this research has a business case, or a societal case, so you can say. So if I just get 0.1% of this figure in my whole career for doing research, I would be very happy. But we'll see whether we get that. Okay, other problems with the data. It's incomplete. Let's say the intrusiveness is blocking in communication, etc. So let's try to make automated reporting of consultations. And there are some, what I completely forgot, that our project is called Care to Report. We need to report in the care sector, but also we care about reporting. These are some design principles, some starting points. I will not discuss them all. But say, for instance, it's very important. There's no interference. So let's say when the patient says, "Okay, my ear is aching," for the recording, it's not clear whether it's the left ear or the right ear. But the video will see that. So that there is no need for the doctor to say, "Well, I see your left ear is aching," just to be hard enough for the microphone to catch that and to have it reporting. That should be not needed, whatsoever you can think of. Very simple, and also report generation in real time. So after the consultation has been finished, the report should be there. Could be finalized or whatsoever, but that's also a very important legal restriction, that we are not storing any video or any other data. We can only store the report, etc. Privacy, correction, checking, etc. Question for you. Do you recognize this architecture? Anyone? Yeah? It has to do with information retrieval, but more precise? Question. It's IBM Watson, the question answering machine of IBM Watson. Next question. Do you recognize this one? Do you recognize this one? Can you read it? Twitter kernel. Do you recognize this one? I see some people nodding. This one? That's our system. What do you see in these systems? Boxes and arrows. And to explain this is our system. You see here, by the way, it was built, Fabian and the two guys are at the back. They laid the fundamentals of it, and there are other students. They did a very good job in the software project. My thanks. But this is a microservice architecture based on the .NET platform. And you see all kind of components, standalone components that embed an AI or natural language component. And that is very typical in this new, let's say, era of artificial intelligence and natural language. Many of you are doing research in that. And you investigate, say, classifiers from human interaction or whatsoever, or you investigate new algorithms for all kind of natural language. And that is good, that's needed. But usually those systems are very, say, standalone, and they work in their own, let's say, research context. But in order to build systems like that, you need to embed them in software components and in pipelines. And that is where the concept of intelligent linguistic information system comes along. What we see is in architecture that the cloud infrastructures are getting immense. All over the world, and in data centers there are services running with data and algorithms and whatsoever. Usually in pipelines of functionality where data has been processed and analyzed and stored for the time being, etc. There is a huge technological diversity. Systems running on microservices in Java, on Python, on any cloud provider. Actually, our system runs with components from Microsoft, Google, and Amazon. And also this technological, we cannot rebuild the system of Google that we want to use. That is, so we cannot have a kind of uniformity in technology. Technological diversity is a given. And also, we want to be future-proof, because we do not know what will, let's say, the major technologies bring in 5 years, in 10 years. So there must be openness and also the service granularity. Do we combine this speech recognition with the triplification or not on one server, or is it on different servers? But also companies like IBM, Twitter, and Google, and all the applications are dealing with these questions. And most of all, the embedding of existing AI and natural language processing. AI and natural language processing, they're very task specific. They can do parsing, or they can do some simple classification or whatsoever. There are very non-trivial computational linguistics, getting all the verbs or framing verbs in their context. We're dealing with open and closed source systems that we want to use. We have several systems, but some run on web services. That's one of our components runs on the web services from Italy. But we also use natural language generation software from from Athens that we need to install. And all these have independent release cycles and API upgrading. When Google releases a new version of Google Speech, okay, we have to do something. And that is with all those components over here, that happens. They have all independent release cycles. And we must be robust for that when we want to run this. Yeah? So you can imagine we have some challenges. So we, in a recent paper we submitted, we defined the notion of a intelligent linguistic information system where the information systems in the middle, and that contains some pipelines that fulfill some function in the context of input systems and context systems and output systems, but also with rules and laws and guidelines that I will show later. But that is how we see that. And we have also some formal definition of that. And okay, so an intelligent linguistic component is a standalone software function that encapsulated AI or NLP processing. So that is essentially such a component that can do triplification for us, or sentence generation, or action recognition. And so, and the pipelines, so the components are in a set, and we have pipelines defined, and then we have all kinds of functions to link the pipelines with the context and internally, but I will not go into details. But this is very important for the definition of the error propagation in pipelines, because you can imagine that when this first component makes some error, there is true positives, but regretfully we also have some false positives, and they have an input, let's say, they are input here, so they have some consequences and the like. They all have some error rate and how to deal with all the propagation, etc. That is in a upcoming paper. And so this is the dialogue summarization pipeline. So when you imagine there is a consultation, then so the doctor and the patient speak, they have a dialogue, and we need to summarize that. It's about a 5 to 7 minutes consultation usually in the Netherlands, with about 1,100 words, and they need to be reduced to about 30 words in the report for the patient. So that's and so we have built a pipeline. So there's first of all the speech-to-text analyzer that outputs a transcript. Then here we go to triples. The triples are three-part thing. Well, by the way, I forgot I have a movie on that. This was built by the students of the software project. Also the movie is theirs. And then we make a formal representation of the semantics of these sentences in triples. Also for all the measurements, and also for all the videos that we are taking. So all are in these triples, subject, relationship, and object. Generate report, and there it is. So this, you see here the report. So family doctors, general practitioners, they report in a convention in 4 classes. So subjective is everything the patient says. Objective is everything the doctor observes or asks. Evaluation is the diagnosis, and the plan is the treatment, so to say. Some medication, or there's nothing wrong with you, or I send you to the medical hospital, whatsoever. And this was obtained in summer, so this is very recent, and this is a world premiere. So this is we are the first in the world to that can generate this. We are very happy that we at least have a proof of principle that is able to make reports of consultation of family doctors with ear infection. So that's the only thing we can handle at the moment. If you have any ear infection, you're happy to be a test subject in my lab, but that's yeah. But we have a proof of concept, and with that we can easily expose our ideas to the medical industry, and they're very excited about that. So that's for the triples. So we extract the triples. Then we need to match the triples with the ontology that is taken from clinical guidelines. So we take guidelines for in this case medical for general practitioners. They are on the website of the Netherlands Association of General Practitioners, the Nederlands Huisartsengenootschap, the nhg.org. And you can simply download them, and you can transform them into some kind of ontology, and then we match the guideline ontology that is over here. You can see you ask for pain, you ask for itching, and then you see how that is being arranged, and try to match that, and then we feed that into the report generation. And we also use the medical graph to that. I'll come back to that later. And then we have the automated generated report. That is the video. So how do we do that? So it's in these 4 classes. So essentially we take multimodal input, microphone, camera, and Bluetooth, that's being recorded and pre-processed